Okay, so we're moving on to Chapter 6. This will be our last chapter of classical mechanics until the second semester when we come back. So Chapter 6 is kind of an interesting chapter because it deals with these two topics, momentum and collisions. So that's the cool part. Collisions mean things run into each other. These are not controlled as what we normally have done. We've dropped things, we've thrown things in the air, we've pushed things along our track. We have hit springs, which are kind of collisions, but not exactly. Collisions are when you don't really recoup the energy. Okay, so the first thing we're going to do is we're going to introduce a new property called momentum. Momentum, not momentum. Yeah, that didn't look right. Momentum. Okay, so we use the small p. Remember, we use capital P for power. We use small p for momentum. And it turns out momentum is a vector quantity. So we're going back to vectors. And it's equal to the mass of an object, which is not a vector, times the velocity of the object, which is a vector. So from vector calculus, a scalar times a vector is a vector. The only time you can get a scalar from a vector is using the cross product, which we haven't talked about yet. We'll talk about it in Chapter 7 and 8, but that'll be next semester. Now the units for momentum, looking at the definition, are kilograms for mass and velocity, which is meters per second. So it's kilogram meters per second. And we don't have a special momentum unit, so it's just kilograms meters per second. So if you double the mass of an object and keep the velocity the same, then the momentum it doubles. And because of the vector nature, you can use the principle of superposition, which we did in Chapter 3 and also in Chapter 4. And the principle of superposition means you can take this vector equation and break it up into the component form. So you can have an x component of momentum, which is the mass, times the x component of velocity. And you can have the y component of momentum, which is the mass, times the y component of velocity. Now kinetic energy, you can do a little manipulation and you can find out that the kinetic energy, you can almost figure it out from units, but kinetic energy is the momentum squared divided by 2m, where m is the mass. Now notice this is not a vector equation because we're taking the magnitude. So this is the magnitude of the momentum. Kinetic energy is not a vector. Okay. Now interestingly, if we go back to Newton's second law said that the net vector force was equal to the mass of an object times the acceleration vector. But the acceleration is equal to, and if you're looking at an average value, it's going to be dv dt, delta v over delta t. If you wanted to do it on an instantaneous basis, it would be dv vector dt. So since mass is a constant, you get that the net force is equal to the derivative of the mass times the vector velocity with respect to time. But m times the velocity vector is the momentum, so it turns out that Newton's second law can also be represented, instead of mass times acceleration, it can be represented as the derivative of the momentum vector with respect to time as well. So this is an instantaneous equation. So what we can do is if you multiply both sides of the equation by dt, then you integrate both sides. So you integrate the dp vector, and you integrate the force vector. In this case, the force, because we're integrating things, the force vector doesn't have to be constant with time. And this integral of dp is just the change in p. So you get p final minus p initial. So that's the change in the momentum. And we call that the impulse. So impulse is a vector as well. So another way of writing this whole thing out is that the, so this is actually delta. Well, no, this is actually not delta. So if we were to take a plot of force versus time, and we have something that looks like this, then this integral, the integral of f dt, is the area underneath this curve. So the area underneath the curve is, so this blue part is the integral of f vector times dt from the initial to the final time. And so another way of talking about this is the impulse is equal to the change in the momentum vector. So that's another thing that we deal with, is if you have a the impulse is the force acting over time. If you remember, work was equal to the integral of f dot dx. So work is the area underneath the force curve with respect to x, whereas the impulse is the area underneath the force with respect to time. So that's our little introduction to momentum. What we did is we defined momentum as mass times velocity. We said that because it's a vector, we can use the principle of superposition. We can break it up into the two components. And we can also take Newton's second law and rewrite it instead of force equals mass times acceleration, that its force is equal to the change or rate of change of momentum. And by then integrating it over a time period, you can relate the area underneath the force versus time curve, which is the integral of f dt, with the change of momentum. And that change in momentum, and also the integral of f dt, is called the impulse. And that's all I have to say about that at this particular point. Say a couple of introductory words about collisions, and then we'll do separate videos for the different types of collisions that we have. So there are two main collisions that we're going to talk about. We're going to talk about perfectly inelastic collisions and perfectly elastic collisions. And the basic concept here is, in a perfectly inelastic collision, the maximum energy is lost. In a perfectly elastic collision, no energy is lost. So our closest example to perfectly elastic collisions are our billiard ball cases, or if we have two objects that have springs on them. So let's say you have an object that has wheels that are perfectly inelastic, and you put a spring on one side, and you don't even have to put a spring on the other side, just so you have some spring. So during the collision, what will happen is this thing, let's group these as it comes along, what will happen, it will touch, and then during this interaction period, the spring will compress, and then they'll stop, the velocity will go to 0, and then it'll expand, and the energy will be recovered. Now the case for a perfectly inelastic collision is this kind of scenario where you have, again, let's assume we have two objects on a cart of some sort, and there's some kind of a coupling mechanism or Velcro, so that when this object comes here, they're all together, when they actually meet, what will happen is after the collision that they'll both be stuck together. So you can think of two cars that have a coupling mechanism. So this one has, let's assume this has some initial velocity. Let's assume this is 0. When they hit, they'll both have the same final velocity. So here, perfectly elastic collisions, what we do is we apply conservation of energy. Which we learned in Chapter 5. This gives us an additional equation that allows us to solve for the unknowns. As we referred to previously, when you have conservation of momentum, you typically have two unknowns and one equation, so you need another equation. The equation used here is conservation of energy, kinetic energy specifically. Whereas in a perfectly elastic collision, what happens is that, let's say we have two objects, then V2 final equals V1 final equals just some final velocity. They stick together. Now, real collisions, like two cars crashing into each other, is really somewhere in between these two. Or just real balls hitting off each other. If you took two volleyballs and ran them into each other, and they would bounce back, there is some energy lost as the material in the ball is deformed and is turned into heat. So we don't really talk about that in this class. There's something called the coefficient of restitution that kind of gauges how perfectly the collision is. So if it's a perfectly elastic collision, then you have a coefficient of restitution of 1. And if it's a perfectly inelastic collision, then you have a coefficient of restitution of 0, and real collisions are somewhere in between. So what we're going to do is we are going to now talk about each one of these separately. So first we'll talk about the perfectly inelastic collision. So let's talk about perfectly inelastic collisions. Okay, so we just referred to these, and basically, let's just give an example. So you got two trains, cars on a train, and let's assume they're both moving with some velocity. We'll call this is 1, this is 2. So we have, this has V1 initial, and this has V2 initial. So that's the initial velocity of each one. And of course, to have a collision, this is going to have to be greater than that. We'll assume that there's plenty of space for this to happen. And there's a mass associated with this car and a mass associated with that car. So this is prior to the collision. So this is initial, and then you have your final. We just drew this a second ago. So after the collision, now you could have this moving in the other direction. So they don't have to be going in the same direction. So this is after the collision. They're stuck together somehow or another. And what will happen is this is moving at V1 final, and this is moving at V2 final. And let's define positive x from left to right. But the key thing is that V1 final equals V2 final, and we just call that V final. They're stuck together, moving at the same speed. So we have two equations. We have conservation of momentum, and what we would be doing is we would define our system to include both of these. So I'm drawing my system as such. Like that. So even after the collision, the system is still like that. So conservation of momentum just says that M1 V1 initial plus M2 V2 initial is equal to M2 V2 final plus, I should have done M1 since that was the order I did it in previously. So you have M1 V1 final plus M2 V2 final, but because the velocity is the same, you get M1 V final plus M2 V final. And you can see that what we can do is we can solve for V final by factoring out V final. And if we divide both sides by M1 plus M2 and do the algebra, you get this expression, that V final is M1 V1 initial plus M2 V2 initial divided by M1 plus M2. And that's it. So typically you're given, you have to be given everything except one item. You have to know the masses, all the masses, and two of the velocities to solve it. So, you could rewrite the problem where you know what V final is and you want to calculate V1 initial. So algebraically you can do that. It's just simple algebra. This is usually the case that we look at where you know what's happening before the collision, and then you want to calculate what the velocity is after the collision. So, I'll give you a couple examples in separate videos, but that's the basic idea. Okay, let's do an example of a perfectly inelastic collision. So what I have is I have two objects, one that's 2,000 kilograms, the second one which is 3,000 kilograms, and the initial velocity of the first railroad car or truck is 20 meters per second, and the initial velocity of the second cart is 0. So it's something moving's going to hit, they're going to stick together like couplings or some way of having them ultimately end up moving at the same velocity. So one thing we have to be careful about is making sure that we reflect the vector nature of the problem. And in these one-dimensional collision problems, it has to do with the sign. So if we're defining x positive going this way, then this is moving from left to right, so it's in the same direction, so it's positive 20 meters per second. Here it doesn't matter because it's going 0. But so that's all that we have to worry about. And because there are no external forces being applied, all the forces are between the two bodies, we know that there's going to be no impulse in this case. And so conservation of momentum basically says that the momentum before the collision has to equal the momentum after the collision. So what we have, and we have to, be diligent about subscripts. So what we have is the momentum before the collision. Well, there's only one thing moving, so we have mass m1 times v1 initial. That's the initial momentum. There is a mass too, but it doesn't have any velocity, so there's no momentum associated with that. And then afterwards, you have object 1, which is going to be moving at, say, v1 final, plus mass 2, which is going to be moving at v2 final. But in the case of inelastic collisions, the final velocities are the same, so we can just replace that with v final. Don't need a subscript since they're both the same. So if we do that, we'll have m1 v1 initial is equal to m1 v final plus m2 v final. You can see I have a constant factor here, v final. So what we can do to solve for v final, we divide both sides by the sum of the two masses. So you get m1 v1 initial divided by m1 plus m2. And now we know everything, so we can go ahead and just solve for the final velocity of the two things, which they're connected together. So you have m1, which is 2,000 kilograms, times v initial, which is 20 meters per second. Momentum is kilograms per meter per second. And then you divide by the sum of the two masses. This is the least efficient collision. You're going to lose kinetic energy because of this. You're not lose at all because they are going to be moving together, but you definitely lose kinetic energy. So if we do the calculations here, it was moving at 20 meters per second, so it's going to be moving less than 20 meters per second after they collide. And I just realized I forgot to divide by something. Just multiplying. So I get 8.0 meters per second. If they were the same mass, this would start at 20, this would start at 0, and the final velocity would be 10 meters per second. So it depends upon the ratio of these masses. If this one's greater than that one, the final velocity will be greater than 10 meters per second. If this one's greater than that one, it'd be less than 10 meters per second. That's what happened in our case. So, other problems, you might be given the final velocity and you have to figure out what the initial velocities are. This doesn't have to be 0. It could be moving this way or it could be moving that way. If you had two objects of the same mass that were moving towards each other with the same velocity but in opposite directions, when they hit, they would just stop. But you can do that all. It comes down to this equation. The inelastic nature is determined by the fact that the final velocities end up being the same.
So now we've talked about perfectly inelastic collisions, let's talk about perfectly elastic collisions. And our collisions are always at one elevation. And even if the collision involves a spring, the initial and final conditions don't involve a spring. So let's use balls in this case instead of little trains. And we're going in one dimension. So this is object 1, this is object 2. This has some velocity V1 initial. This has some velocity, V2 initial. And then they collide. So they're going in this direction, and then they collide. But during the collision, there's no loss in energy. So after the collision, let's just clone these things here. What do we want to do here? Clone. Oh, didn't want to do that. Well, that's fine. I can pull this down. It's just been easier to draw them. And we'll delete those two things. So after the collision, they may be going in opposite directions. We take into account the velocities in terms of the sign. So even though I'm showing this going from right to left, I'm assuming that we're going to define everything as positive in the equation, and when we know the actual directions, we can define it another way. So this is then going to be V1 final, and then you have V2 final. So we've got two equations, conservation of momentum, which is exactly what we had previously. We won't be able to combine the two final velocities because they don't stick together. So you have M1 V1 initial plus M2 V2 initial. That's our initial momentum. And if this is going from right to left, then this is going to be a negative quantity. And then you have M1 V1 final plus M2 V2 final. So that's conservation of momentum. And if we gave you the two velocities initially, then the two unknowns would be V1 final and V2 final. So we only have one equation, so I have to come up with another equation. So the second equation is conservation of energy. And so we have the kinetic energy of object 1 initially, which is 1/2 mv squared. And then we have the kinetic energy of object 2 initially. So that's our initial kinetic energy. Notice we square them, so these are both going to be positive quantities. And then you have M1 V1 final, that's your final kinetic energy for object 1, and 1/2 M2 V2 final squared. So we still have the same two unknowns, V1 final and V2 final. We have two equations, but it's not two linear equations, so it's not quite as simple. Now, it turns out, and I'm going to derive it in a separate video if you want to watch it. It turns out that you can simplify conservation of energy after some math, and it says that V1 initial minus V2 initial is equal to negative V1 final minus V2 final. So we'll have two equations, this equation and that equation, and so these are two linear equations. You might have these two as your unknowns, V1 final, V2 final. You can use substitution and then solve for it. You can use elimination, but typically you use substitution. These will be known. You solve for one of these unknowns here, plug it back in here, then this equation, instead of having two unknowns, has one unknown. So that's the basic idea. That's conservation of momentum and conservation of kinetic energy for this type of collision. So if you want to see the actual derivations in your book, but sometimes that's hard to follow reading it, so you might just want to watch this. Okay, so this is a derivation of the equation that we just presented for kinetic energy for a perfectly elastic collision. So what we start off with is conservation of momentum. You've got two objects before the collision, you've got the same two objects after the collision. They have different initial velocities and different final velocities. conservation of kinetic energy, you've got the kinetic energy of object 1, kinetic energy of object 2. Initially, these are the kinetic energy of object 1, finally the kinetic energy of object 2 finally, and you can see that we can cancel out the 1/2 first step. Then what you can do is you can group the two terms together that involve m1. So you'll have v1 initial squared. Actually, no, that's not true. So what we're doing here is we are taking conservation of momentum and just rearranging that. So we take this term, v1 final, move it to the left-hand side. So it becomes m1 times v1 initial minus v1 final. And then we take this term, move it to the other side. So you have this term, m2 v2 final, and then you have m2 v2 initial. So we're just rearranging the terms for conservation of momentum. Okay, so let's see what we do next. And we can do the same thing for conservation of energy, it looks like. So we have m1 v1 initial squared, m1 v1 initial squared. Then we take this, move it to the other side. So that's m1 v1 final squared. And you can do the same thing for the m2. So you've got m2 v2 final squared minus m2 v2 initial squared. Okay, so that's the next thing you do. Now, what are we doing now? So then you can factor this. So this is the kinetic energy thing. So this is like, you know, you've got a squared minus b squared is equal to a minus b times a plus b. So the inner and outer cancel out. So I can make this go to that. So I'll have v1 initial minus v1 final, and then v1 initial plus v1 final. And then you can do the same thing over here. So you've got v2 final minus v2 initial, and then v2 final plus v2 initial. But if you look here, v1 initial minus, from conservation of momentum, I've got m1 v1 initial minus v1 final, and that's equal to m2 v2 final minus v2 initial. So that's m2 v2 final minus v2 initial. So these are the same thing, and so they can cancel out. And all you're left with now is this part, v1 initial minus so what you end up with, this canceling and that canceling out, you've got this term, and then you can rearrange these terms. So this term you leave on the left-hand side. This one comes from here, goes to the other side, becomes minus. Then you have this on the right-hand side, v2 final, and you subtract v1 final. So I'm just rearranging this, and that finally you can factor out a negative sign here. So instead of v2 final minus v1 final, you have negative v1 final minus v2 final. And that's the equation that we use. We don't have to rederive this anytime. So when you get these inelastic collision or elastic collision situations where you have conservation of kinetic energy, we use this formula, which is conservation of momentum, and then this formula, which was originally conservation of energy but simplified by using conservation of momentum. And so you have linear equations in the variables, and ultimately what you need to do is you can specify everything except two variables, and you can then use substitution to solve for the unknown variable. Okay, so let's do a perfectly elastic collision. So this is my problem. I've got an object moving from left to right at 2 meters per second of 2 kilograms. I've got a second object moving right to left at 1 meter per second, so it's negative 5 kilograms. You just need to figure out what the final velocities are given those initial velocities. So this is conservation of momentum,
M1 V1 initial plus M2 V2 initial. So those are the initial momentums is equal to the final momentums. The conservation of energy is kinetic energy is V1 final minus V2 final is equal to negative V1 initial minus V2 initial. I did this problem just a minute ago and I wrote this down wrong and I got the wrong answer, so reworking it now correctly. So what we can do is we can plug in the numbers that we know. So this is 2 kilograms, 2 meters per second, 5 kilograms, negative 1 meter per second, 2 kilograms times V1 final, and 5 kilograms times V2 final. And this part is wrong, so let me fix that. So that's where I made a mistake. So we got V1 final, which I don't know, minus V2 final, which I don't know, is equal to negative V1 initial, which is 2 meters per second, minus V2 initial, which is negative 1 meters per second. So I get V1 final, still working on the same equation, minus 2 V2 final is equal to, so we got 2 minus a minus, so that's positive 3, but then we have the negative out in front, so it's 3 meters per second. Okay, so we're going to solve for V1 final. V1 final is going to be equal to V2 final minus 3. I've removed the units now. Now I can substitute this into this equation. But before I do that, let's rewrite this without all the units. So you're going to have 4 minus 5 is equal to 2 V1 final plus 5 V2 final. So we get negative 1 is equal to 2 V1 final plus 5 V2 final. And then if I substitute this in for V1 final, I'll get 2 times V2 final minus 3 plus 5 V2 final. And if we multiply everything out, we'll get 1 is equal to 2 V2 final minus 6. So 2 times negative 3 is negative 6. Plus 5 V2 final. And if we add 6 to both sides, we'll get 5 is equal to 7 V2 final. 5 plus 2 is 7, and then you can divide both sides by 7. So you get V2 final is 5/7 meters per second. And then you can go back to this substitution to find V1 final. So it's equal to V2 final minus 3. So V2 final is 5/7 minus 3. So that's 21/7. 21 minus 5 is 16. So it's negative 16/7 meters per second. So that's V1 final. And so initially V1 was going this way and V2 was going this way. And when it's over, V1 is going this way. It's going negative. So this is V1 final. This is V1 initial. And V2 final goes the opposite way. It's positive. It was originally negative. So that's 5. This is V2 final. So V1 final is equal to negative 16/7, and V2 final is 5/7. And we can kind of double check just by figuring out what the initial momentum was. So the initial momentum was 2 meters per second, I think, right? Is that what it was? 2 meters per second times 2 kilograms. Okay. So 2 times 2. And then we had 5 times negative 1. So that's 4 minus 5. So it's negative 1. The units for momentum are kilograms meters per second. Mass times velocity. Now if we take the second condition, we still have 2 kilograms times V1 initial. V1 final is negative 16/7
sevenths plus 5 times positive 5/7. And so there we'll get negative 32/7 plus 25/7. 32 minus 25 is 7, but because this is negative and this is positive, it's negative 7. So you get negative 7/7, which is negative 1 kilograms meters per second. So you can see that the initial momentum is equal to the final momentum. So when you work this problem, you got these sevenths things, you're like, what's going on? But now I feel better. Okay, the last thing we're going to look at, it's kind of a misnomer in some ways. I'm calling it an explosive collision. So in this case, we've been having things running into each other. But you could have two things that are together, and then they're not connected to each other. So if one of the objects is propelled to the, say in this case, let's say object 1 is propelled by throwing something or by shooting something to the left, then the part 2, which is not connected to it, is going to go to the right. So you can think about recoil from a gun. And if you have a frictionless surface, what will happen is that this thing initially is not moving, and then both things will be moving in opposite directions at constant velocity. So if you look at conservation of momentum, you got the same thing that we've had before. The initial momentum, m1 v1 initial plus m2 v2 initial. So that's the initial momentum. And then you've got the final momentum, m1 v1 final plus m2 v2 finals. But in this case, 1 and 2 are initially not moving, so there's no initial momentum. So the whole left-hand side is 0. And all you have is the right-hand side. So if you know the two masses and you know the velocity of one of them after something happens, then you can figure out what the velocity of the other one is going to. This one goes to the left and this one has to go to the right because these have to sum up to 0. So since the masses are always positive, the only way that you can get one positive and one negative is to have one of the velocities positive and one of the velocities negative. Now typically you know both masses and one velocity and you solve for the unknown velocity. So in this case I'm going to have this person that's standing on some ice or in space, someplace that's frictionless, and this person is going to so it's in space. Okay, so there's a person in space and all they have that's loose to their possession is they have their cell phone. They're out there checking their Facebook page while they're working and they're like, oh, I got disconnected from the space shuttle. What am I going to do? How am I going to get back? So what he does is he throws the cell phone to the left, and as a consequence, he's going to go to the right. So in our case, we have this person who has a mass of 80 kilograms, and the cell phone is only 1 kilogram. And he throws the phone as hard as he can, and it turns out the phone is moving at 20 meters per second. So the question, there's two questions here. One is, what is his velocity after he throws the cell phone? And then how long does it take him to get, he's say 30 meters away from the spacecraft, so how long does it take for him to get there? Well, that one's easy. Once you know the velocity, you can take the relationship between velocity and time and distance to figure that out. But let's use conservation of momentum, and what that's saying is that m1 v1 final plus m2 v2 final equals 0. So we're going to call the person object 1, the phone object 2, so we can just plug in. So we have m1, which is the person, 80 kilograms. So you got 80 kilograms times v1 in final plus m2, which is the phone, 0.1 kilograms,
times 20 meters per second. So if you solve for V1 final, it's just going to be 0.1 kilograms times 20 meters per second divided by 80 kilograms. So you get 0.1 times 20 divided by 80. And so the velocity is 0.025 meters per second. It's negative, because when you move this to the other side, it becomes negative. So in this case, I guess I'm defining x positive to go to the left, since I said this was positive 20. Or I could have defined it the other way, made that negative 20. The key thing is they're different signs. So remember, displacement is equal to velocity times time if the velocity is constant. And once he throws the cell phone and he's let go of the cell phone, he's going to be moving at this velocity. And there's nothing to slow him down. It's not very fast, but he's just going to keep going through space. So all you have to do, I'm just going to take the magnitude, 0.025 meters per second, and times the time. Actually, that's what I'm trying to solve for. So that the time is the unknown. 30 meters is the distance. So you get time is equal to 30 meters divided by the velocity, 0.025 meters per second. So 30 divided by 0.025, that's 1,200 seconds. Time, let's see, hours, so divided by 3,600 seconds per hour. So it's a third of an hour, which is 20 minutes. So it's not too bad, really. I mean, I think you can stay calm for 20 minutes. These things could be moving tens of thousands of miles per hour around the Earth. But because they were originally traveling at the same speed, then even if they get separated by distance, they're still going to travel at the same speed relative to each other. So he really doesn't have too much to worry about as long as he has something to throw to move him in the opposite direction. Now, of course, the tricky part would be aiming this thing, because if he aimed it off center a little bit, not exactly opposite to the spacecraft, he could end up floating this way, and then he'd miss the spacecraft, and he'd keep going forever, and he'd get further and further away. So it's a little dangerous maneuver. At least here he's 30 meters away, so he's not any further than that. But so how would you do that philosophy of making sure you don't miss the spacecraft? Yeah, that would be difficult. You'd have to save something here to maybe correct your course as you got closer.
Okay, the last part of Chapter 6, there's only 4 sections in Chapter 6. Well, actually, it's the 5th one, but we don't really cover that. At least I haven't in the past, so I have to think about that. So what we have is what's called glancing collisions, not conditions. Glancing collisions. So this is kind of a two-dimensional situation. So we still have two objects. They're not quite aligned. Actually, let me, since they're the same ones, I'm going to make sure they're the same size. Now they don't have to be both. They don't have to be in this simplified version, but I guess it's easier in this case. So we're going to have this moving. We're going to have this one stationary, and then after the collision, this one will be going this direction, and this one will be going that direction. So we'll call this object 1, object 2. This is object 1, object 2. It's just basically what you do when you're playing pool. So let's just add a page and look at this collision a little bit more detail about what's going on. So we'll take that and let's make this a little bit bigger. Okay, so what happens is it comes along, it hits this ball. And that there's actually the force is going to be transmitted exactly like that between the two. So the force is not just in the x direction. There's going to be a force in the x and y direction. So you're going to have some momentum coming in, and during the collision there's going to be this, you'll have these will deform, and then they will undeform, and after the collision you'll get one object that's moving up to they'll still both be moving from left to right because the initial momentum is from left to right. So you have to have the final momentum has to be going from left to right. And then you have one moving up, one moving down. So the after velocities are going to have two components. They're going to have an x component and a y component. Likewise, down here, you're going to have an x component and a y component. So what we'll do is we'll call this V1 initial. V2 initial is equal to 0 meters per second. And then we have V1 final. There's a V1 sub x final. And I'm just going to move these over a little bit because they're running out of space. And then we have a V1 y final. And then we have V2 x final and V2 y final. So you get a lot of subscripts. So the first subscript is which object, second subscript is what direction, and the third subscript is whether it's initial or not. Now, initially V1x initial is equal to V1x. There is no y component. There could be a y component, just makes the thing more complicated to solve. That's what you do when you're playing pool. You're just trying to figure out by looking at the collision of the balls, which way is this ball going to go. And because this one has some initial velocity, typically you look for the ball and try to imagine where this point of contact is, and then you draw a line through that point of contact, through the ball, and that's the direction it goes. So typically when you're playing pool, well, when you're playing pool, there's only one moving ball. So as it comes and it hits this, you can imagine this line of sight, and then imagine where that collision is, and the fact that the forces acting right here are going to be right in that direction. So if this has a force acting on it during the collision, then the ball has to go in that direction here. Now this one is more difficult because there's a force acting on it, but there was also an initial momentum, so it doesn't go exactly where you think it does. That's part of being good at playing pool, is to know where this ball goes. And there are other things, backspin, etc., that affect where the ball does go. So it's actually easier to figure out where this ball is going. The hard part is where the initial ball that you're hitting initially with the Okay, so typically we're talking about a perfectly elastic collision. Otherwise, it becomes very difficult. So it's a perfectly elastic glancing collision. So if we apply conservation momentum to this, what you do is you use the principle of superposition. which just basically means you break up your components, your velocity into the components. So you've got your x component. Now I'm going to go component. I'm going to assume that we actually have x and y components of both these two balls, just to be on the general side. So you'd have, for the x components, you'd have m1, which is a scalar. So you take the total mass of this object and you multiply by v1 x initial. And then you multiply that by m2 times v2 x initial. So that's your initial momentum in the x direction. And then you do it in the y direction, the after. So the only thing that changes is that initial becomes final. So that's conservation of momentum in the x direction. And then you can do the same thing in the y direction. So you have m1 v. So it's exactly like this, except I change y, x to y. Okay, x becomes y. This tricky part of collisions, you've got to really be careful about subscripts. Make sure you don't make any mistakes. Okay, so that's conservation of momentum. Now for our special case here, this is 0, and this is 0, and this is 0. And then if you have an angle, let's call this theta and call this phi, then you can use the, you could rewrite this as, v1x final is going to be equal to v1 final times the cosine of theta, and v2x final is equal to v2 final times the cosine of phi. Likewise, if you look at the y component, you would see that v1 y final is not actually, this should be the cosine. Yeah, that's right. So v1 final, y final is v1 final times the sine of theta, and v2 y final is equal to v2 final times the sine of phi instead of theta. So you have to know something about the direction. You have to have this direction determined, and then once you know the directions, then you can solve it. So I'm not going to go through. So that's the conservation of momentum. The conservation of energy is 1/2, the initial kinetic energy is 1/2 mv1 initial squared. That's the initial kinetic energy of the object 1, and then you get 1/2 m2 v2 initial squared. So that's my initial kinetic energy is 1 equal to my final kinetic energy and notice I don't have to worry about direction here. I just take the actual velocity. I don't have to worry about the principle of superposition because energy is not a vector equation. So there's no vectors involved, there's no components. You just use the total velocity in both cases.